Alrighty, so this is where it all starts to come together. This is where we look at our two-step differentiation process, which we've been doing recently with bringing the power down and reducing the power by 1 for polynomials. And we look at our average rate of change and our instantaneous rate of change, and we see how it all ties in together and how we can use that. So sometimes we refer to this as the limiting chord theorem. Why we do that will become apparent fairly shortly. It's also known as differentiation from first principles. So I'll talk about that, and right, let's jump straight in. Okay, so we've already gone through this several times, just to refresh everyone's memories, that when we're determining the rate of change at any point of a function, we're finding the gradient of the tangent. So the gradient of the tangent to the curve. So for example, if we wanted to find the gradient of this point at point P, so gradient of this curve, at the point P, so that's the rate of change, we want to find the gradient of that tangent of the black line. And we know we can do that by approximating between, say, this point P and Q1, and then as this gets smaller, then it gets closer and closer and more accurate there. So let's have a look at this one. This is a parabola, a good old parabola. We've got y equals x squared. All right, so we're going to say, well, this point here is, we'll just say it's x. Okay, which means that this point here is going to be x squared. Now we're going to assume that we've added some value h here, some distance. Okay, so that means this is x plus h, and this is x plus h squared. Okay, so just the x value squared. So if we want to work out the gradient of that line, so this red line in here, we need to do the difference in the height over the difference in the horizontal. So the gradient is going to be x plus h squared minus x squared, because that's that difference there, that minus that, all divided by, and it's just divided by h, because that's that difference there, which you can see if you have x plus h minus x, it just leaves you with h. Okay, so let's expand this out and see what happens. So we get x squared plus 2xh plus h squared minus x squared all over h. So just doing a bit of algebra here. Okay, that goes with that. Now I've got an h here and an h squared, so if I factorise that out, h out the front, 2x squared plus h, still over h, ooh, I can cancel that out, excellent, and now I'm left with 2x plus h. Okay, so that's our formula, or rather our equation for the gradient at any point on this curve. Okay, so we've got 2x plus h. Now we're happy with the x, but we've still got this h kind of hanging out there, so let's see what we can do with that. Okay, so obviously we had, so the gradient, don't do that yet. So we had the gradient was 2x plus h. Okay, now this gets more accurate as h gets smaller. So just flicking back here, obviously as this distance gets smaller and smaller and this point B gets closer and closer, then this gets more accurate as an approximation of the tangent to the curve. Okay, so we can say that this is as h tends towards 0. This is a key here. So we limit as h tends towards 0. So if we sort of talk about limit as h tends towards 0, then obviously this is going to become 2x, okay? Because that h gets smaller and smaller and smaller until it's insignificant, it's effectively 0, so this is 2x. So therefore we generalise, and we can say, well, the derivative, because that's what we're doing, is finding the derivative, finding the gradient. The derivative of x squared is 2x from here. Now, hang on a minute. If we did that with our two-step process, so where we went f of x is x squared, and f prime x is, we'll bring the power down to reduce the power by 1, we get the same thing. So, is it a coincidence? Let's explore a little bit further and see. So let's have a look at this one. Okay, we want to do this by first principles. So when it says by first principles, it means using that, that limiting idea. Okay, so we're talking about having a point x and a point x plus h. Okay, so f of x is just this. Let's put in f of x plus h. Okay, remembering that we're just going to replace everywhere we have an x, we replace with an x plus h, so it'll be x plus h squared plus 2 times x plus h. Okay, so if we had that on our parabola, where we had 2 points, so this was x, and this is x plus h. Okay, so those are the x values, and then we can work out the y values, the corresponding y values. Okay, so this is the corresponding y value, the function value for this point. Alright, so all I've done is substitute x plus h in there. Okay, so the derivative is going to be the difference between those points. So that minus that, which means x plus h squared plus 2 outside x plus h. I'll put that in big brackets so you can sort of see what's going on. Minus x squared plus 2x. And that's all over h, all over that difference in there. Now, this takes a little bit of expanding and so on, but if you work it all out, we'll just do it quickly here. We've got x squared plus 2xh plus h squared plus 2x plus 2h minus x squared minus 2x, being careful with your signs in there. Okay, now that x squared gets rid of that one, that 2x goes with that one. Alright, what we end up with is 2xh plus h squared plus 2h. We can factorise the h out of there. That leaves us with 2x plus h plus 2h. Oops, sorry, no, not 2h, that h doesn't go, we factorise that out. Okay, so 2x from there, h and 2 over h, those cancel. So what we're left with is 2x plus 2 plus h. Okay, and again, if we limit that as h tends towards 0, then we get 2x plus 2. Let's go back up and do our two-step process. Okay, f of x is x squared plus 2x. F prime x is, bring that down, 2x plus 2. Are they the same? Yes, they are. So we can apply this to any function at all. It doesn't matter what the function is, but we take a function, we define a point P such that the x value is x, and therefore the y value is f of x, and then we talk about this point Q where it's x plus h, so this distance here in there is h. Okay, and then we've got f of x plus h, that's over here. And then we just reduce this and make it smaller and smaller. So what you get is f prime x is just f of x plus h minus f of x, that's the distance, the difference in the y values, over h. Okay, and this works for any function. And this is what we call differentiating by first principles. Okay, it's actually the formal definition of the derivative. So when you're talking about a derivative of a function, this is what you're actually doing. You're taking this limiting chord theorem and you're working it out as h tends towards 0, as that distance in the horizontal tends towards 0, and that gives you your derivative. So let's do another one, just for fun. Okay, so we've got f of x. Let's work out what is f of x plus h. Okay, and this will just really convince you that our cheating, our little shortcut really works. Alright, so we've got 2 minus x plus h cubed. Okay, so you can bring that one out. And now the derivative is going to be, so it's this one, 2 minus x plus h cubed minus 2 minus x cubed all over h. Now your binomial expansion will come in handy here in Pascal's triangle. And if you do that, you get 2 minus x cubed plus 3x squared h plus 3xh squared plus h cubed, so that can come in handy, save you a bit of working there. Take 2 plus x cubed, multiplying through that bracket there. Okay, and then if you multiply that bracket through and start cancelling things out, you end up with negative 3x squared h take 3xh squared take h cubed all over h. Okay, factorising out and cancelling gives you minus 3x squared take 3xh take h squared. And of course, if you limit that as h tends to 0, gets rid of that entire term because that becomes 0, that entire term as well, negative 3x squared. Okay, if we did it the short way, f prime x equals, obviously this will be 0 because it's a constant, and this one is negative, bring the power down, 3x squared. Same. Okay, so hopefully what that's done there is shown you where this comes from, but also shown you the power of using the shortcut, of using our bring the power down, reduce it by 1, rather than having to differentiate by first principles all the time. So now let's look and see how we can do it even more simply with ClassPad. Okay, so there's a number of ways you can do this. The first one is you can actually do the limit, do the working out through first principles if you really want to. So we can define our function as 2 minus x cubed. Okay, and if we define that, cool. And now we can actually do the limit. So if you go to keyboard, I think it's keyboard 2, math 2. Yep, look at the limit there. And we say limit h, as h tends to 0. Let's put a fraction in here. And we want f of x plus h minus f of x over h. Oh, look. Okay, so it'll do the derivative from first principles, okay, from the theorem. You can also use through the calculate, you can use calculate menu. You can use differentiate. So if we just do f of x, and you don't have to define a function first for this one. You could have just done this bit. Do f of x calculation diff. Yep, that looks good. Same thing. Okay. And just to convince you once and for all, we can actually do this with x to the power of n. So to generalize any polynomial term, so x to the power of n, doesn't matter what n is, as long as it's an integer. Let's differentiate that. Calculation, differentiate. There we go. So that's where we bring our n down. So bring the power down, multiply it, reduce the power by 1. So that should have you feeling very happy about doing the shortcut version of differentiating there. Okay, so what the derivative gives us is an equation to find the gradient at any point on the curve, which means we can then use that gradient and the point itself, so whatever this x value is, to find the equation of the tangent to that curve at that point. So of course the tangent is a straight line. This is the gradient of the point of the curve, or of the curve at that point, and then you can work out this one here. Okay, so how we do that? We have a look at this example. So don't worry about first considering the gradient. Okay, we know we can do the shortcut version now. So what we're going to do is say, well, let's find dy dx, okay, is 2x minus 2. Alright, so when x equals 3, then the gradient, or dy dx, is going to be 2 times 3 minus 2, or 4. Alright, so what it means is at this point, the gradient there is 4. Okay, so if you drew a straight line through there, that's white. That's not very clear, is it? Let's do that in blue. Okay, so if you drew a line there, the gradient of that line would be 4. And now we can work out what the actual equation of that line is, because what we've got is y equals mx plus c. You know that the gradient is 4. And then you can substitute that point in. So 3 is 4 times 3 plus c. Work that out. You get c equals minus 9. And I'm just going to pause there for a second, and we'll continue just the last little bit in the next video.